It's okay.
Okay.
Do you want me to move
Thank
forward
you.
or backwards? Or...
Thank you.
Okay. Your head's blocking up the camera.
You could if you want.
What's that about?
It's okay. It's okay, Robbie. I can hear them. Like.
Rachel, if you need anything, just speak up.
Okay, you can do it. You can do it, Robbie.
Yeah.
Can you flip your hands over like that?
Yeah, she just can't touch them together.
Well, I don't think. Yeah, I just can't. My forearms can't leave the
so many
ground.
more numbers to you did I only give two?
I'm good.
Was I trying
Please,
to save
I'd like it
time?
actually decent.
Obviously not, because now I appear to be wasting time talking about it. Do you think that it would be too hard for me to remember all those numbers? Well, obviously not, because I just did it. So I will tell you
Okay,
why.
good.
When you're doing experimental calculations, there's two kinds of numbers. There's exact and measured. Exact numbers are like the number of seconds in a minute, or the number of eggs in a dozen. They're defined that way, and thus we know them, in effect, all the way out to an infinite number of decimal places. If I say that there are a dozen eggs, you know that that's 12. It's not 12.0000000001 or 11.9999999. It's 12. But that's not true for the number of miles per hour my car was going. That car wasn't going 60.0000 out into infinity miles per hour. I only know the speed of my car to 2 decimal places because that's all I get from the speedometer. So the car could have been going 59.8739003 miles per hour or 60.49321289 miles per hour. The speedometer would still say 60. And no matter how well I measure the car's speed, I will never know it at the same level of precision that I know the number of eggs in a dozen. So that's the second type of number, measured numbers. Now the cool thing about measured numbers, because you never ever know them exactly, is that they tell you two things at once. First, they tell you the number that was measured.
Robbie, could I have
and
the
second,
mouse?
they tell you the precision at which that number was measured. People often get their heads all tangled up about this, but with a measured number, you just have to remember that the actual number goes out to infinite decimal places. You just never know all of them. You can't. It's impossible.
Mouse,
So when
please.
my scale says 175 pounds, that doesn't mean 175.00000 pounds. It means 100.
I'm 100 years old, and I want to tell the world
It's
what
okay.
I
That was a
have
very,
learned.
very.
Hello,
boring video.
I'm Hank Green. Welcome to Crash Course Chemistry. Today, we're talking about the most important table ever. Not the table where they sign the Declaration of Independence, nor any table of contents, nor this table right here, nor the stone table of Aslan. Nay, it is the periodic table of elements, a concise, information-dense catalog of all of the different sorts of atoms in the universe. Today I want to talk a bit about the creation of this table, which is, to be clear, one of the crowning achievements of human thought. To start out, though, let's close our eyes and pretend. Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know, downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck, or extreme, insane, undeniably Russian persistence would have it, they accept you, and your saddle-worn butt, as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dmitri Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Not the table where they sign the Declaration of Independence, nor any table of contents, nor this table right here, nor the stone table of Aslan. Nay, it is the periodic table of elements, a concise, information-dense catalog of all of the different sorts of atoms in the universe. Today I want to talk a bit about the creation of this table, which is, to be clear, one of the crowning achievements of human thought. To start out, though, let's close our eyes and pretend. Imagine you're in Siberia, and you're a 13-year-old boy, and your father, who was a professor but had gone blind, leaving your family of more than 10 brothers and sisters destitute, has just died. I know, downer. Your mom, to support the family, has reopened an abandoned glass-making factory in the small town where you live, largely because she wants to make enough money to send you to school someday. A year passes, the factory burns down. But your mom, she sees your potential. She knows that you have a keen scientific mind and will not see that squandered. So, with your siblings out of the house and on their own, she packs up your belongings, straps them to a horse, and with you in tow, rides 1,200 miles through the Ural Mountains on horseback to a university in Moscow. There, on your behalf, she pleads earnestly and effectively, and they reject you. So together, you ride another 400 miles to St. Petersburg, to the school where your father graduated as a scientist, and as luck, or extreme, insane, undeniably Russian persistence would have it, they accept you, and your saddle-worn butt, as a pupil. Your mother, having completed her mission, promptly dies. If you're doing your imagining as I've told you, you might feel a tremendous debt to your mother and a very deep desire to ensure that you achieve something on par with the sacrifices she made for you. And maybe that's one reason why Dmitri Ivanovich Mendeleev became the crown jewel of Russian science and a theorist who revolutionized how we see the world. Mendeleev spent a great deal of time in laboratories as a student, studying the burgeoning new field of chemistry. He worked with all the elements that you could work with at the time, and his knowledge gave him unique insights into their properties. Those insights would come in handy. Let's all imagine we're Mendeleev again. I like doing that. And that we know a bunch of stuff about chemistry, which, you don't yet, but we're imagining. So it's the 1860s, and about 60 elements are known to mankind, and their atomic weights are mostly known as well. So the simplest thing was just to sort them in order of their atomic weights. But interestingly, you, because you're clever pants, realized that the most significant relationships seem to have nothing to do with the atomic weight. Lithium, sodium, potassium, and rubidium were all extremely prone to reacting with chlorine, fluorine, iodine, and bromine. Beryllium, magnesium, calcium, and strontium were all similar but less reactive. But with a quick inspection, you, and to be fair, a number of other chemists, realized that there was a relationship between atomic weights, but it's periodic. At the beginning of the list of elements, characteristics repeat every 7 elements. On a side here, we now know that it's every 8 elements, but in the 1860s, elements were studied based on their reactivity. So the non-reactive noble gases had not yet been discovered, so the period occurred every 7 elements. As the mass of the elements increases, the repetition starts to look a little less periodic, though it's certainly still there, it just isn't perfect. Some of your colleagues, they're saying, well, such is life. It was perfect repetition early on, but later in the list it gets a little fuzzier. But not you. You become obsessed with the perfection of the periodicity. You write out the names and weights and properties of elements on cards, you lay them across your desk, shuffle them, tear them to pieces in frustration until one day you realize that you're simply missing cards. The numbers aren't working, not because there's something wrong with your ideas, but because some elements simply haven't been discovered yet. Armed with this insight, you insert gaps into the table, and things suddenly fall perfectly into place. 7 element periods for the first 2 rows with hydrogen in its own category, 18 element periods for the next 2 rows. You're so certain that you predict the properties of these missing elements. And when a French scientist comes along and says that he has in fact discovered one of them, you argue with him, saying that you discovered it first in your mind. And when you see his data and it doesn't match yours, you publish a paper saying his data for the new element he discovered is wrong. That's how certain you are of yourself and this beautiful new theoretical framework you've created. And you know what the really crazy thing is? You're right. That French guy's data was wrong. You, never having examined the element he discovered, knew more about it than he did. Because you are Mendeleev. master of the elements. Okay, we're done imagining for the episode. That was fun, though. The different groups Mendeleev had identified are a lot of the same groups that we study today. Starting at the left, we have the soft, shiny, extremely reactive alkali metals. So reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkali metals want nothing more than to dump off an electron and form a positive ion or cation.
Robbie?
And they're always jonesing to hook
What's
up with a
this
hottie from
ductile
the other
mean?
side of the table. So, of course, seeing
Can you
they're so
Google it?
reactive, you don't find hunks of them lying around in nature.
So I prefer that's applying to ducts. Yeah, ducts. We'll quarantine.
Starting at the left, we have the soft, shiny.
Well, alkali metals are very reactive, malleable, ductile, good conductors.
Oh, they can be made into.
Oh, okay.
Ductile. It is able to be drawn out into a thin wire.
Oh,
Formed
yes.
without losing toughness, pliable, not brittle.
Okay, thank you, man. Sorry.
No problem.
Extremely reactive alkali metals. So reactive, in fact, that they have to be stored in inert gases or oil to prevent them from reacting with the atmosphere. Alkali metals want nothing more than to dump off an electron and form a positive ion or cation. And they're always jonesing to hook up with a hottie from the other side of the table. So, of course, seeing as they're so reactive, you don't find hunks of them lying around in nature. Instead, chemists must extract them from compounds containing them. Next, you have the alkaline earth metals. Reactive metals, but not as reactive as the alkali metals, forming cations with 2 positive charges instead of just 1. Calcium, shown here, undergoes a very similar reaction to sodium and water, just a little more slowly, producing a little less heat. The middle body area of the table is made up of a nice solid rectangle of transition metals. These are the metals you think of as metals, with iron and nickel and gold and platinum. The majority of elements are metals. They're fairly unreactive, great conductors of heat, but more importantly for us, good conductors of electricity. They're malleable and can be bent and formed and hammered into sheets. And they're extremely important in chemistry, but overall surprisingly similar to each other. On the far right, just over from the noble gases, the halogens make up a set of extremely reactive gases that form negative ions or anions with 1 negative charge and love to react with the alkali and alkaline earth metals. The rectangle between the halogens and the transition metals contain a peculiar scattershot of metals, metalloids, gases, and nonmetals. These guys don't end up as ions unless you take extreme action and start shooting other ions at them. So generally, a bit boring over here, though lots of interesting covalent organic chemistry. We'll get to that. Down below, in their own little island, are the lanthanides and actinides, metals that were largely undiscovered in Mendeleev's day because they're so similar that it's next to impossible to separate them from each other. And finally, on the far, far right, also undiscovered when Mendeleev built his chart, the completely unreactive noble gases. Like a lot of other obsessive scientists, Mendeleev never thought he was done with his table, so he held it back for quite a while, only publishing it as part of a new chemistry textbook he was working on as a way to make some quick cash that he needed. And as with many other scientific revelations, there were a number of other people hot on this discovery's trail. As many as 6 people published on the periodicity of elements at roughly the same time as Mendeleev, but a few things set him apart. One, he was obsessive. He knew the data better than anyone else and had spent a ton of time working on a theory that many people thought was just an interesting little quirk. And 2, he realized in a way no one else did that the idea of periodicity had far-reaching consequences. It seems as if he had a deep belief in the cosmic importance of what he was doing, almost a religious fascination. Mendeleev believed in God, but also he believed that organized religions were false paths to the unknowable nature of God. I like to believe that he thought he saw some divine pattern in his tables, and Mendeleev felt as if he was coming to know God in a way that no other man ever had. To be clear, this is pure conjecture. And as we now know, the periodicity of elements is a physical phenomenon. It's a function of electrons, which are in some ways pretty dang peculiar, but certainly not at all mystical. But we'll get to that peculiar physical reality in the next episode. The periodic table that we know and love, I love it anyway, is a representation of reality, a way of understanding and sorting the universe as it exists. But that form of the table is not by any means set in stone. Indeed, a contemporary of Mendeleev envisioned the table set onto a screw or cylinder with the elements wrapping around from one side to another. While Mendeleev's table looks more like a map up on a wall, de Champ-Courtois, a geologist, envisioned more of a globe. Unfortunately for de Champ-Courtois, no publisher could figure out how to print his cylindrical 3-dimensional table, and so he published his paper without a graphical representation of his periodic cylinder of the elements, and it was largely ignored. I guess they didn't have papercraft back then. I am a huge fan of this cut and tape model of the periodic table. You can make your own, there's a link in the description, and there are also a ton of other designs for periodic tables that have various advantages over the one that we're all familiar with. Our periodic table as it stands is really a little bit unhappy with itself, frankly. The lanthanides and actinides really should be part of the table, but we separate them out because it's hard to fit that on a piece of paper. Really, this is what it should look like. And really, it would be best if it wrapped around into a circle so that fluorine and neon and sodium were all next to each other instead of being on the opposite sides of the map, because they're just one proton away. Mendeleyev's contribution, nonetheless, is more powerful than at first it seemed. He ended up forming a guide to help future chemists understand things that wouldn't be discovered for 25, 50, even 100 years. Indeed, after Mendeleyev's theories were published and accepted, the overwhelming cry from the scientific community was, why? Why? And though Mendeleev was not himself concerned with this stuff, he actually denied the existence of atoms, or indeed anything he couldn't see with his own eyes. It turned out that the answer to the first why was the electron. That sneaky little electron, Mendeleev, if he'd been around to see their discovery, he would have hated them. But you will have a healthy respect for them after you learn all about them on the next episode of Crash Course Chemistry. Thank you for watching this episode of Crash Course Chemistry. If you were paying attention, you now know the terrible, beautiful, and wonderful story of Dmitri Mendeleev, how he organized the elements into the periodic table, some of the basics of the relationships on that table, why Mendeleev stood out from his colleagues, and how the table as we know it today could stand some improvement. This episode of Crash Course Chemistry was written by myself, filmed and directed by Caitlin Hoffmeister, and edited by Nick Jenkins. The script was edited by Blake DeFestino and Dr. Heiko Langner. Our sound designer is Michael Aranda, and Thought Cafe is our graphics team. If you have any questions, please ask them in the comments below. Thank you for learning with us here at Crash Course Chemistry.
Okay. I wanted to see what it looked like between my toes.
Looking good, Rachel.
Thank you.
She wants to see what it looks like between her toes?
Yeah.
I'm 100 years old, and I want to tell the world what
Thank
I have
you.
learned.
Live for now, because life is good. You make it good.
You will learn not to cheat.
There are miracles all around you.
Stay young.
Always tell the truth.
Keep your eyes open and sometimes your mouth shut.
Don't complain.
Tell it like it is.
Don't bitch.
Hesitate and you lose.
Put the pedal to the metal.
Live fast.
And never, ever forget where you came from.
Hello, I'm Hank Green, and welcome to Crash Course Chemistry.
Yeah, there's two foods. And one of them already did. I said, yeah, use 12 guns. And they were like, where's the gun? And you say, what?
Since it left it quite hurt.
It was a plus, right? That's a little bit of a stretch to leave right from the Maps and other keep seeking balls back. Why'd you have to come over here?
Because otherwise they're so fast. They work
You're not really good at control.
That's nice, man. That's nice to hear that. No. Yeah, we moved out here.
Is that the one set? You should see the stuff I got go by. The only way I can do the work on one computer is if I keep doing all back in the I don't think it's okay either. No. It's got to be like 6 now. I have been like small 6s. No, 2 days of closing. I'm in the same area. So, yeah. Yeah, set it up.
I know what the deal are. How big what those go. Checking the
I'm just getting out my own figuring out how much. Regular.
Okay. Well, do you have to do the check-in station and all that? You see, that's part of why yeah, on same deal. So you could just go in there and well, I gave up the phone.
Thank you.
You go with Tracy? Same thing. It's got a lot of see if you can go on.
I can smile.
Now you're making me like the north shore of South Florida.
Good. I'm going to skip that, okay?
Maybe when I'll get back into it.
If you want any of this, feel free. I can literally use it.
That's how it's That's it. And patience. Because you screw what you screw in around. Then the deer goes right over the tree just left. So I usually go, scope it out, and I always climb, I prefer to climb the cherry tree. Because the cherries have that free bark. It doesn't matter. You can climb it. Easy. Try to climb something. Push or something. You know what I mean? You can do something one time. You can do people who just get hands he gets nice sauce. And they got like 2 beers. They got recipes. Really good. Speed is just the one that always some of the time they should
Our best deal ever.
By now, you're probably starting to see how chemistry can change your view of the world. Chemistry explains everything you can see, how it looks, the way it feels, why it behaves, the way it does, by describing everything that you can't see. It helps us understand the biggest stuff in the universe by helping us understand the tiniest. And that's why chemistry can be kind of hard to understand sometimes. Because we are, on a chemical scale, huge. Chemistry traffics in infinitesimal particles, but we are made of quadrillions of those things. They are the building blocks of mass. We are literally massive. So mass is how we massive beings tend to understand the world. In our day-to-day dealings with substances, we need to have some sense of how much of it there is before we can use it or predict how it's going to act. For example, chemistry will be happy to tell me that the atomic structure of the sugar in this packet is 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms in every molecule. But I don't have any idea how many molecules of sugar I want to put in my tea, or how that one molecule will react with other chemicals in my body. To understand that kind of stuff, I need to know the mass of the sugar that I'm dealing with. In other words, I need to measure it. And that is why there's stoichiometry, the science of measuring chemicals that go into and come out of any given reaction. In Greek, it literally means measuring elements, and in essence, it allows us to count up atoms and molecules by weighing them. Stoichiometry, yes, contains a fair bit of math, but it's one of the most important decoders that we have as chemists. It's what we use to translate from the very small to the very big, to parlay the stuff that we can't see into the stuff that we can. And because of that, chemists use it all the time.
My one leg is a little frozen.
Yes, tea.
Oh, it's cold?
No, it's kind of frozen. I mean, like, if I stop, I know I'm going to have a Charlie horse, so.
Now, if you've been with me for a couple of weeks, and I do hope you have, you're probably thinking to yourself, wait, no, don't we already have a way of measuring elements? And you're right, we do. The real coin of the realm when it comes to measuring stuff in chemistry is relative atomic mass. The average atomic mass of all of the naturally
If anyone had, like, a little bit of coffee.
So, for example, all the natural carbon on Earth occurs as one of 3 and only 3 isotopes, C12, C13, and C14. They all have
I do have
protons,
caffeinated tea sometimes, so it would be nice to have just a tiny sip
show
of
up on our
something like
planet
that.
in totally different proportions. So the relative atomic mass of carbon is a
But
weighted
coffee is
average of these 3
amazing.
masses, which comes out to 12.
It's a wonderful idea.
12.01 what? Well, remember when we were talking about units of measurement, we're talking about arbitrary talk. Most units, except for the ones that we use to measure time, aren't based on any real objective value. We just pick a unit, like a kilogram, and we agree for a standard on what a kilogram is, and then we run with it. The same goes for atomic mass. We measure atomic mass.
Well, actually,
in
Robbie, you
atomic
could
mass
move it
units.
if you'd like.
We made them up, and the value for a single AMU is, bear with me now, 1/12 of the mass of an atom of carbon-12. Why? Funny story. Until the mid-1800s, chemists in different parts of the world used different yardsticks for measuring elements. One of the most intuitive, and therefore most common, was to use the smallest, simplest element, hydrogen, as a baseline. But in the 1850s, some chemists, led by German Wilhelm Ostwald, proposed using oxygen instead. They preferred oxygen mainly because it combined readily with so many other elements, so they figured it would be easier to determine the weights of lots of compounds. So a bunch of guys stroked their beards, agonized over this for years, until in 1903 they decided that atomic weight, as it was called, should be measured in 1/16 of an oxygen atom. Until in 1912 isotopes were discovered and chemists realized that you can't talk about an element like it's all the same thing. It turned out there was an oxygen 16 and an oxygen 17 and an oxygen 18. And suddenly, everyone was
Mommy,
walking around
my
like,
right leg
I don't
is
know
a
how much
little-
this stuff weighs
Ah.
anymore. This was so crazily disruptive that it took
I don't
another
know.
50
Is there anything
years
that you can
of
do to stop
strokey
a
beard
Charlie
meetings
horse?
for
Because it's
everyone to
really,
decide
I'm
to
gonna
use
have a
another
Charlie horse as soon
standard.
as this thing
Carbon
finishes.
12. Like
And I
oxygen,
just can't
carbon
move
is
it at
common
all
and
because
kind of
it's
promiscuous
so,
when it
the
comes to
Charlie
what
is
it bonds
creeping.
with. And since it has 12 protons and neutrons, the mass of other similar elements could
Only
easily be
thing I think you
expressed
can do
as
is
some
when you
fraction
do
of
a
it.
stretch.
So since
Keep your legs
1961,
stretched.
science has pegged one
You know what I mean?
AMU as 1/12
You have to
of an
stretch
atom
it.
of carbon 12, which means that carbon has a relative atomic
Okay.
mass of 12.01 AMU. Oxygen 16
No, I mean, if I
AMU,
stop, I'm
and
going to have a
hydrogen
Charlie horse, but I can tell it's
1.008
gonna,
AMU.
it's
So
kind
that's
of
how we weigh
creepy.
As
atoms.
soon as you're done, I would
But
sit
none of
and
this
stretch.
solves my
Sit on
tea
your
sweetening
butt
problem. Like,
and
I don't know how
stretch
many
your
AMUs of
hands
these
to
molecules
your toes.
together are gonna make this taste
You know what
good
I'm
to
saying,
me,
right?
or how many
That will
molecules
stretch
of
your,
sugar I can consume while maintaining my
muscles
slim
back
yet
there.
robust physique. This doesn't happen by itself, you know. In order to make these calculations and predict reactions, I first need to be able to convert the atomic mass of this sugar into a standard amount of substance. Not weight, not volume, just purely objective amount of stuff. You heard me. Stuff. That, my friends, is what moles are for. Not those moles. Those are nice-looking moles. A mole is arguably the most important unit in all of chemistry because it allows us to express a chemical's atomic mass in terms of grams.
What?
And to define what a mole is, no
That
matter
might
what
be
it's a
nice,
mole
just
of,
to,
we
well,
use our old
I would like,
standby
Mom, do you have
carbon
anything
12.
slightly
There are
caffeinated?
6.022 times 10 to the 23rd atoms in 12 grams of
Oh,
carbon
okay.
12, and by definition, that number of anything is a mole
Oh.
of that thing. That's a lot, and it is known as Avogadro's number, one of the most important constants in chemistry, and although Avogadro isn't the one who arrived at this number, it's named in his honor because he used this basic principle of comparing amounts of substances to first weigh atoms and molecules. So there are this many carbon atoms in a mole of carbon 12, and there are the same number of anything in a mole of anything else. Like a dozen roses is 12 roses, but a mole of roses is 6.022 times 10 to the 23rd roses, which would be enough roses to cover the surface of the earth quite deep. A mole of sand would be 6.022 times 10 to the 23rd grains of sand, and if they were each 1 millimeter long, a mole of them would stretch 100 quadrillion kilometers. So you get the picture? It's a big number. But in chemistry, the thing to remember is this. A mole of any element contains 6.022 times 10 to the 23rd atoms of that element, no matter what. This is what lets us translate numbers of atoms into grams. It lets us weigh the elements. All right, follow me here. 1 mole of carbon 12
Okay.
contains 6.022 times 10 to the 23rd atoms.
Yeah.
It weighs 12 grams, right? So 1 mole of oxygen also contains 6.022 times 10 to the 23rd atoms, but because oxygen atoms are more massive, it weighs 16 grams. And you'll recall that oxygen's relative atomic mass is 16 AMUs. The number of atoms per mole remains the same, but the mass of a mole depends on the average mass of the element. This simply means that 1 mole of any element equals its relative atomic mass in grams. So now you got it. 1 mole of hydrogen weighs 1.008 grams, a mole of iron is 55.85 grams, and a mole of natural carbon is 12.01 grams. This is known as an element's molar mass. And now that we know the molar mass of elements, we can calculate the molar mass of any compound. All we have to do is add up the molar masses of its component elements. So for instance, the formula for this sugar, or sucrose, is C12H22O11. 1 mole of sucrose, by definition, contains 6.022 times 10 to the 23rd molecules, and since each molecule contains 12 carbon atoms, 22 hydrogen atoms, and 11 oxygen atoms, then 1 mole of sucrose contains 12 moles of carbon, 22 moles of hydrogen, and 11 moles of oxygen. Multiply the number of moles of each element by its molar mass and add them up. That's the molar mass of the whole compound. See, the mole is like our chemical Rosetta Stone. With it, we can translate anything from the level of atoms and molecules to the level of grams and kilograms. And we can use it to describe not only elements and compounds, but reactions. And you don't need a lab full of samples to do it, just a pencil and a calculator. To get back to my tea problem, let's say, hypothetically, that I'm watching my weight. So I want to know what it'll take for me to burn a certain amount of sugar that I consume. That's a reaction, and it's a pretty simple one. My body uses sucrose by combining it with oxygen to create energy plus CO2 when H2O is waste. You can write this out as an equation in which the reactants combine on the left to yield the products on the right. But there's a problem here. This equation doesn't reflect chemical reality. During a reaction, bonds are broken and new ones are formed, but the number of atoms of each element remains the same. The sugar and oxygen molecules may be busted apart and mixed up, but the number of each kind of atom that you start with ends up being exactly
My
the
right
same
leg,
after
though,
the
is
reaction.
going to
Conservation of mass,
definitely,
yo.
by the
So when
end of
writing a
this,
reaction
if
out as an
not, I'm
equation,
hoping
the
it
number of
doesn't
atoms of
during
each
this, it's
element
gonna
has
have
to
a
be the
Charlie
same
horse
on
like
both
anything.
sides. Reconciling the reactants with the products is called equation balancing, and it's a good bit of what stoichiometry is all about. Because from a chemical perspective, an unbalanced equation is pretty useless. It doesn't tell you how much is going in, and it doesn't tell you how much is coming out. Without balancing the equation, it's like saying when a mommy and a daddy love each other very much, a baby appears, and that's all you need to know. But that's not all you need to know. So how do you do it? Not make a baby. Balance an equation. I did biology last year. Well, the best way is to start with the most complicated molecule, which in this case is, of course, the sucrose. For every molecule of sucrose that goes into the reaction, you know that you're going to have 12 carbon atoms. So right off the bat, you know that you're going to have to end up with at least 12 molecules of CO2 as a product, because that's the only molecule where those carbon atoms end up. Now let's deal with the hydrogen, because that also only shows up in one molecule on each side of the equation, so that's easier. You know that at least 22 atoms of hydrogen go into the reaction, and the product contains some multiple of 2 hydrogen atoms.
Thank you.
That's the H2 water molecule. So if there were 11 water molecules produced, that would balance the hydrogen. 22 hydrogen atoms on each side. Finally, the oxygen. Since we know we have 12 CO2 molecules and 11 water molecules as product so far,
Maybe a little.
we also know that we're going to end up with 35 oxygen atoms. If you look at your reactants on the left, you see that you have 11 oxygen atoms in the sucrose molecule and 2 in the molecular oxygen.
Can you look at my leg and tell me how
Carbon
it
and
is?
hydrogen are balancing nicely with only one
My right
molecule
leg.
of sucrose, so let's leave that alone. But there could be any number of paired oxygen atoms involved. Since you need 35 and you know you have 11 to start with in the sucrose, you just need 24 more, which would equal 12 molecules of O2. And now the reaction is balanced. You know exactly what my body is producing. For every molecule of sucrose I'm metabolizing, I have to inhale 12 molecules of oxygen, and in return, in addition to a little sugar buzz, I'll produce 12 molecules of carbon dioxide and 11 molecules of water. This is incredibly useful in helping us understand the proportions of chemicals as they react at the molecular level. But in a lab or in life, you have to work with measurable amounts of stuff. So the last stoichiometric trick you need up your sleeve is to calculate specific masses of the reactants and products. So for instance, how much oxygen will I need to inhale in order to burn 5 grams of sugar? To figure that out, we just need to focus on the left part of the equation because we only need to quantify the reactants. First, convert your balanced equation into molar masses. In order to get from molecules to grams, you have to go through moles first. When you figure out the molar masses, you see that the ratio of sucrose to oxygen is actually pretty close, 384 grams of oxygen for every 343.3 grams of sucrose. Then you simply compare this ratio to the masses of reactants in your experiment, 5 grams of sugar with X grams of oxygen. And hopefully you know how to solve for X. For every 5 grams of sugar I ingest, I'll need to inhale 5.6 grams of oxygen, which I happen to know is about 35 breaths worth. So as long as I manage to stay alive for the next minute and a half or so, I'll manage to burn off this 5 grams of sugar down the hatch. Today, we learned about 2 of the most important units of measure in chemistry, atomic mass units and moles. We also learned how to calculate molar mass and how to balance a chemical equation. And finally, we talked about how to use molar ratios to calculate the amount of stuff that goes in and out of a reaction. Thank you for watching this episode of Crash Course Chemistry, which is filmed, edited, and directed by Nick Jenkins. This episode was written by Blake DiPestino and edited by Dr. Heiko Lankner. Sound design is by Michael Aranda, and our graphics team is Thought Cafe.
Yeah, man. It recorded for 1 hour. Over an hour.
Equinox from Chevrolet, first and only car company.
It falls from the sky. It makes up 60% of our bodies, and just about every chemical process related to life takes place with it or in it. Dihydrogen monoxide. Without it, none of the chemical reactions that keep you alive would happen. None of the reactions that sustain any life form on Earth would happen. Not even the majority of inorganic chemical reactions that shape the surface of the Earth would happen. Water is the key. to nearly everything, and one of the reasons it's the key is because it's really good at dissolving stuff. We need it so bad that we dump over 180 gallons of it into our bodies every year, and we do that in order to maintain an aqueous or water-based solution inside our cells, because aqueous environments are pretty much the best for cool chemistry. Each and every one of us uses water for all kinds of chemistry every single day. Our body chemistry, our food chemistry, and yes, our laundry chemistry all take place in water.
Can I have some more water, Rob?
Ugh. This used to be a white sock. It is now a little bit of gray sock, and in places a little bit of a yellow sock. But anyway, I want it to be white again, and to do that, I'm gonna need some chemistry. To whiten whites, you might use a solution of sodium hypochlorite, better known as bleach. What makes bleach so good at its job is that it's a really strong oxidizer, meaning that the oxygen atom is really good at pulling electrons away from other compounds, making them break apart. This is really handy for getting rid of stains, but as you can tell by the formula, sodium hypochlorite also contains chlorine, which happens to be really good at killing things. That's why we use it in swimming pools and as a disinfectant. But there are lots of other good oxidizing agents, and one that doesn't contain chlorine is hydrogen peroxide, and it can be used as a bleach too, but its only components are hydrogen and oxygen, just like water. We'll talk about oxidation and other kinds of reactions in a couple weeks, but before we get to that, you have to understand solutions. And before we do that, I'm just gonna get rid of the laundry because it's kind of stinky. This bottle of hydrogen peroxide contains a solution. And not just the solution to my problem of stained laundry. By solution, I mean a solution of liquid with another substance dissolved in it. Here, water is the liquid or solvent, and hydrogen peroxide is the solute or dissolved material. And water is an amazing solvent, possibly, arguably, the best solvent on Earth. Why? A lot of reasons. There's a lot of it on the surface of the Earth. That helps. Just abundance is good. It's liquid at a very wide range of temperatures, and being liquid is what you need to be able to be a solvent. But also because it's polar. It's a very polar molecule. Remember how I said that oxygen is really good at pulling electrons toward it? Well, oxygen atoms are more electronegative than hydrogen. The oxygen atom pulls harder on the molecule's electrons than the hydrogen does. As a result, the electrons in a water molecule tend to spend most of their time near the oxygen, giving the oxygen end a partial negative charge and the hydrogens a somewhat positive charge. This polarity makes water extremely effective at dissolving things, especially other polar things. The sugar we mixed into our tea last week, for example, was polar. When you mix a polar solid like sugar into a polar liquid like water, the molecules of the water surround the sugar molecules. The negative side of the water molecule is attracted to the positive side of the sugar molecule and vice versa. And interacting with the sugar molecules, the water inserts itself between all of the individual molecules of the sugar that were once clumped together in the sugar crystals. A liter of water can dissolve as much as 1,800 grams of sucrose. Water-based solutions. Earlier, I called them aqueous solutions, and I'm calling it an aqueous solution again so that you remember it's called an aqueous solution. Aqueous. You can create all sorts of aqueous solutions using salts or minerals, even acids. Ethanol, which composes 95% of this grain alcohol, is polar, so it dissolves easily in water. But water does not dissolve non-ionic, non-polar substances. Oil, for instance, doesn't have any polarity, so it has no interest in interacting with water. So when you mix them, they separate. Water's polarity also gives it lots of other super useful properties. For example, water can decrease the attraction between ions of different charges. We call this its dielectric property. Take table salt, for example. It's made of positively charged sodium ions and negatively charged chlorine ions. When it's mixed with water, the water dissolves the salt into its component ions. The water molecules then surround the individual ions and shield them from each other's electric charges. These ions in water are called electrolytes, literally loosened electricity, because separating them through dissolution frees them to act independently and carry their electrical charge around. You've probably heard about electrolytes in biology class, but you've definitely heard about electrolytes in Gatorade commercials. Your body needs electrolytes to carry electrical signals that help your muscles twitch and your brain cells fire and get all the business of living done. In addition to helping you live, electrolytes are one of the most important ways chemists have of classifying solutions. Pure water on its own does not conduct electricity, which seems a little weird to us, the whole hair dryer in the bathtub thing still being a terrible idea. But if you put a bit of salt or any other ionic solid in the water, they dissolve into those component electrolytes. It's the electrolytes that are conducting the electricity.
I told you,
Now,
Dad,
as you
my
might
right
expect,
leg is
but we
scaring the
have
heck out of
Swedish
me.
physicist Svante Arrhenius to thank
I'm feeling
for
fine
figuring
except
this
for
out.
that.
While doing his doctoral research in the 1880s, he first developed the idea that a solution's electrical conductivity could be linked to the concentration of ions in the solution. It was one of his predecessors, British super genius Michael Faraday, who discovered that substances dissolved in water conduct electric currents. Faraday was terrible at naming stuff, though, so he wrote to a guy who was known for coining terms, William Whewell. You may have heard of his most famous creation, the word scientist. Whewell wrote back to Faraday saying, "I would propose for the two elements resulting from electrolysis the terms anion and cation, and for the two together, you might use the term ion." And there's something interesting here, and I didn't pick up on it at first, but Whewell said the things resulting from electrolysis. Faraday thought that the electric current is what produced the ions. What Arrhenius discovered was that water simply dissolves certain substances, like salts, into their constituent ions, which themselves carry the charge. And since electrolytes carry electric charge, the higher the concentration of electrolytes in a solution, the higher its electrical conductivity. Arrhenius found that you can even reverse engineer your study of a solution and by measuring its electrical conductivity, figure out how concentrated it is. Despite the importance of his work, Arrhenius's chemistry professors didn't think much of it, and he got a mediocre grade, which is why it must have been particularly sweet when he won the Nobel Prize in 1903 for that very same research. Today we know a little bit more about how electrolytes work, and we've learned that the relationships between their concentration and their conductivity is not always straightforward, because not all electrolytes dissolve equally well in water. A strong electrolyte, for example, is one that dissociates or breaks apart completely when dissolved in water and conducts electricity very well. Salts do this, so do strong acids like hydrochloric and sulfuric and nitric acid, as well as strong bases like sodium and potassium hydroxide. Weak electrolytes only dissociate partially when dissolved in water, so they're only somewhat conductive. Most of the solutes molecules stay stuck together, remaining neutral. Acetic acid, the active ingredient in vinegar, and ammonium hydroxide are examples of this. And of course, some things dissolve in water but don't conduct electricity at all because they don't dissociate into ions. Alcohol and sugar, for example, are non-electrolytes. Now, what does any of this have to do with my laundry? Well, hydrogen peroxide is a polar molecule, so it dissolves really well in water. But it's a very weak electrolyte. When it dissolves, it tends to dissociate into a water molecule and a lone oxygen ion. Since the dissolved peroxide creates even more water, the concentration of ions is quite low. But that lone oxygen ion is not happy by itself. It goes on an oxidizing rampage, swiping electrons from anything it can find. It's especially good at tearing up the tricky double bonds that tend to give laundry stains their color. When that rampaging ion destroys the double bond, the stain disappears. We're used to thinking of hydrogen peroxide as a fairly mild chemical, but that's because the over-the-counter stuff is pretty dilute. Too much peroxide could actually dissolve my clothes, and some of my favorite shirts are in here, so we need to dilute this stuff to make the solution the right strength. And as you might expect, if you joined me on my recent foray into stoichiometry, when chemists think about the strength of a solution, they think about moles. So before we can dilute this formula, first we have to figure out how many moles of solute of hydrogen peroxide we're working with here. You'll remember, I hope, that 1 mole of a compound equals 6.022 times 10 to the 23rd molecules. That is a big number. So to make it easy on ourselves, we usually figure out how much a mole of a particular substance weighs. In our case, a mole of hydrogen peroxide weighs 34.04 grams. The number of moles of solute that are in a solution is known as its molar concentration. That's also known as the solution's molarity. As a rule, molarity equals the number of moles in the solute divided by liters of solution. So a 1 molar solution contains 1 mole of solute per 1 liter of solution. Do not confuse this with another way of measuring concentrations based on mass instead of based on volume. This is known as molality, and it's expressed as the number of moles of a solute in a kilogram of a solution rather than in a liter. Molality refers to moles per unit mass, and molarity refers to moles per unit volume. Sorry, scientists are bad at naming things. thing sometimes. You just have to remember this stuff. So now that we know what molarity is, let's figure out the molarity of this hydrogen peroxide solution. The label on the bottle says a 3% solution weight per volume. Technically, that's terrible chemistry
water,
because
please.
it's expressing a percentage in terms of two different sorts of units, but it does let us know how much solute went into the solution, 30 grams of H2O2 per 1 liter of water. I mean, just to be clear though, it makes no sense to have a percentage with two different units, and
this Charlie
maybe
horse is
these
gonna be
folks
so
need to
bad.
watch some Crash Course Chemistry. So to calculate the molarity of this solution, we first need to figure out how many moles of hydrogen
just don't wanna
peroxide
tap this
are
Charlie
in
horse,
30
but I'm gonna have
grams
it
of
right after
hydrogen
I'm done.
peroxide. If we divide the 30 grams in the solution by its molar mass of 34.014 grams per mole, we find that we have 0.88 moles of hydrogen peroxide per liter of solution. Or, so you get used to the lingo, a 0.88 molar solution of H2O2 in this little brown bottle. Now that we know the molarity of the original formula, we can start thinking about how to dilute it. To dilute a solution, you either have to add more solvent or reduce the amount of solute. Since I'm already starting with the solution, I need to add even more solvent, water, probably in this tub right here, so let's just get that out of there. Now there's a handy chemical rule for understanding dilutions. The moles of solute before dilution is equal to the moles of solute after dilution. Think about it, the total amount of hydrogen peroxide is going to stay the same, no matter how much water it's diluted with. But as you dilute a solution, its volume grows. The moles stay the same, and its molarity thus shrinks. To calculate precisely how much one affects the other, we use a standard and super simple dilution equation. Here, M1 and V1 are the molarity and volume of the original concentration, sometimes called the stock solution. In this case, it's what's in the bottle. M2 and V2 are the molarity and volume of the diluted solution. So in our case, M1 equals 0.88. That's the molarity of the hydrogen peroxide solution that we've got. And to bleach the stains out of laundry, we need a 0.1 molar solution. That's M2, the molarity that we want to get to. And the tub that I'll be soaking my whites in holds 38 liters of liquid, so that's our V2. All that's missing is the volume of peroxide solution that we must add to 38 liters of water to get to our target molarity. Do the math and you get V2 equaling 0.24 liters of hydrogen peroxide, or 250 milliliters. And we just fill this right on up here. Hopefully we have enough. And that's what we need. And while I wait a few hours for the peroxide to do its work, I'm going to enjoy another of my favorite aqueous solutions, tea. Today here at Crash Course Chemistry, we learned about some of the properties of water that make it so special, its polarity and its dielectric property. We learned how electrolytes can be used to classify solutions, and we discovered how to calculate a solution's molarity, as well as how to dilute a solution using the dilution equation. This episode of Crash Course Chemistry was written by Kim Krieger. The script was edited by Blake DiPastino and myself, and our chemistry consultant is Dr. Heiko Langner. Our director, cinematographer, and editor is Nicholas Jenkins. Script supervisor is Michael Aranda, who also is our sound designer, and our graphics team is Thought Cafe.
I told you my leg is going to die and it's killing me. I'm so scared. I hope it doesn't do a Charlie horse soon.
Do you want to stop?
How do you stop a Charlie horse from coming? That's all I need to know.
Don't stop a Charlie horse from coming. No, do you want to stop? I don't want you to.
Our best deal ever. The Optimum Triple Play with free multi-room DVR and a free speed upgrade. Only $84.95 a month for 2 years. Stay connected with unlimited data access at over 1 million Wi-Fi hotspots. The Optimum Triple Play, just $84.95 a month.
All right, so you're studying chemistry. What's the worst that can happen? In most classes, the worst that can happen is just abject total failure. Just like failing a test, failing the class, having to rethink your life choices, maybe even quit, drop out of school, get a job at a diner, and start smoking Lucky Strikes. But in chemistry, the worst thing that can happen is death. And I don't want to make light of this. Labs are dangerous places. Chemists die younger than the average person, both because of workplace accidents and cancer caused by exposure to chemicals. But chemists have also done more to increase the average lifespan of humans on Earth than, in my opinion, any other profession. So it's a necessary hazard. Last week we talked about stuff mixing together, and that's important for sure. But today, and for the next few weeks, we're going to talk about the actual reactions happening in those solutions. Dangerous reactions, atoms reorganizing themselves to create whole new substances. These are the processes that make our world the world that we know and love. Some of them are benign and beautiful, some of them are face-meltingly terrifying. And that's not hyperbole, I mean actual melted faces. Captain John Mullen, there, he blazed the first wagon trail across the Rocky Mountains into the interior Pacific Northwest. The captain's only been standing in this spot right here for about 75 years. And look what's happened to his face. I know this maybe isn't the face melting you were expecting, but we're not so gruesome here at Crash Course Chemistry. The sorry state of Mr. Mullen's face here is the result of an acid-base reaction, one of the three major types of reactions that happen in solution that we'll be talking about here at Crash Course Chemistry. And the acid that did this was mostly sulfuric acid. Now you may be wondering, who's been coming by and throwing sulfuric acid on statues? Well, actually, what's been doing the throwing is clouds, the sky, though the actual source of the sulfuric acid, that's 400 miles away at the Colstrip Power Plant in Colstrip, Montana, and also at coal-fired power plants all over the United States. The United States of America burns about 1 billion tons of coal per year, and most of that coal is mined right here in the U.S. Montana, where I live, is home to the Powder River Basin, a geographical location responsible for 40% of America's coal output. Between 50 and 70 freight trains ship out of the Powder River Basin every day. Each train has at least 115 coal cars and is more than 1.5 miles long. And all of this coal burning, it has effects, significant effects, acidic effects. But first, what exactly are acids and bases? Well, acids, sour. So sour, that's the first thing that we learned about acids, actually, and that's why acid, actually means sour in Greek or Latin, and acids are excellent at dissolving stuff. They kill things and melt your face. What about bases? You might have some idea of what a base is. Bitter tasting, slippery, like soap. Soap is, in fact, a base. And bases, like acids, are totally dangerous and can melt off your face. They're also like the anti-acid, basically. In fact, they're in antacids. If you mix acids and bases together, they neutralize each other. But as with most things in chemistry and in life, when it comes right down to trying to define exactly what something is, it gets weird and messy and confusing and terrible. So, forget everything you ever learned about acids. Wipe the slate clean. The most common acid on Earth is water. What? And water is also the most common base. And am I saying this purely to confuse you? Yes. Well, mostly to convince you that the world is way more complicated than you thought it was. In 1923, two guys simultaneously defined acids and bases in the exact same way. Bronsted and Lowry defined them. They didn't classify them by how they acted or what they tasted like or even what they were made of.
You too.
They defined them. And this was an impressive feat because a huge class of molecules, to some extent or another, act as acids and bases. So to come up with a definition that fit all of them, that was not so simple. Bronsted and Lowry defined an acid as being anything that donates a proton and a base as being anything that accepts a proton. And when we say proton, what we're talking about here is a hydrogen atom without its electron. Usually this is happening in water. Acids and bases can react in a gas, but almost always they're in an aqueous solution. And when a proton gets donated in water, it is accepted by water. And H2O is converted into H3O+, the hydronium ion. So when an acid is added to water, it dissociates, like any other ionic compound, forming H3O+ and a negative ion. The acid has donated a proton to the water. Also, a little chemistry terminology thing, we usually just write H+ or say protons in solution, when in fact we are referring to hydronium ions. It's just a shorthand. In reality, H+ in aqueous solution is always H3O+. Let's take a look at the dissociation of hydrochloric acid for some more terminology bits here. You see right off the bat that the HCl is donating a proton, but with many acids, particularly weaker acids, the reaction can actually go back the other way, with H3O+ donating its proton. So in this situation, every chemical in the reaction, also sometimes called the major species, can be called an acid or a base. On the left-hand side, the water is accepting the proton, so it's the base, and HCl is donating it, so it's the acid. And on the left-hand side, the Cl- would be accepting the proton, so that would be the conjugate base, and the hydronium ion is the conjugate acid. The phrase conjugate acid always used to confuse me because I thought it had something to do with conjugating verbs, but it's actually the older original sense of the word, the one where conjugal or marriage-related visits for prisoners come from, which means joined together. For every acid, there is a conjugate base, and for every base, there is a conjugate acid. Previous definitions of acids and bases, particularly the one proposed by our old friend Arrhenius, relied on specific major species, most notably our friend the OH or hydroxide ion. And while hydroxide is in most bases, it's not in all of them. For example, ammonia acts as a base when it reacts with hydrochloric acid to form ammonium chloride. There's no hydroxide, but there's definitely proton donation and acceptance going on. Now, acids and bases are not all created equal. Certain acids really like to get rid of their protons and will only reluctantly convert back from their conjugate base by accepting the proton. We call them strong acids, and the conjugate base is a weak base. The same can be said for strong bases and their weak conjugate acids. The reason why all of the most interesting acid-base chemistry happens in water is that dihydrogen oxide is really great at being either a base accepting a proton from an acid or an acid donating a proton to a base. Thus, water is the world's most common acid and also the most common base. So, what does any of this have to do with power plants in John Mullen's face? When coal is burned, the sulfur in it reacts with oxygen to form sulfur dioxide. That sulfur dioxide then reacts with water and oxygen in the air to form sulfuric acid. When that sulfuric acid rains down, a set of acid
You dare disturb my techno?
Yes, I did. I dared disturb the thing. Should we go off?
Is that what that was?
Yes, that was Japanese techno pop.
Horrendous.
Phantasm Brigade, come on!
Yeah, I know you were telling me about this.
This is the good techno. I haven't even gotten into the bad techno yet.
It's worse.
Well, that was good techno, what you just heard.
As far as I know, it wasn't good techno.
Depending on your taste level, it either gets better or worse. So, but yeah.
She shattered her. I hope they don't go into competition. That would blows me away. Said she would become a regular. Some mother of that's like.
Mom, do you think, is there any way I could have like pretzels or something? Because I know this Charlie horse is going to come and I just really want my leg to be able to.
As far as I know.
Or Mom, I don't know, what would you say is the best to prevent a Charlie horse? Should I just keep doing what I'm doing and then just.
Salt would be a good idea.
Okay, maybe I should just have salt, pure salt.
Well. Do you want to just go? What about these saltine crackers? There's salt on the saltine crackers.
Well, maybe I just, never mind, I'll be good.
Do you want the saltine crackers? They're right here.
I just can't move my right leg it's really.
Well, when you finish, either way, whether you make it to the time or not, we're gonna have to stretch you right out.
I know.
You have to sit on your butt and do like, your hands to your toes.
Okay, I can't take any more of this without techno.
I'm 100 years old, and I want to tell the world what I'm
Don't worry, this one gets better.
That actually sounds pretty good to me.
Oh, it gets good.
Good as in it will annoy me?
Good as in like
Is that good water? Is that salted?
Yes.
Oh gosh, thank you.
No problem. How are you feeling?
Like my right leg is gonna die by the time this is done.
You're at an hour and 32 minutes. You just have less than an hour left.
Wow, really?
Yes, you're going through victoriously. If you want to play Pokemon later, like, you know, it's dictate to me and fish do.
Thank you. See, it's getting good.
There you go. Look at it that way, right? Maybe Robbie should be a gym teacher because he shows up in shorts every day.
かく溶けて消えるわ土の国闇が降りる東の空赤く染まった風に揺られ儚く消えてゆくはたった一つの光沢灯火にあまねく世の場
Can I have clean water?
そっと残して今すぐに時放て心持ち悪くさいを今すぐに時放て
Wipe the hair from my face, please, Robbie. 意味知れとも変わらずに That Charlie horse is gonna destroy me. Please, yeah. I know. Pain's temporary, pride is forever.
You want to sit
Yes, please. Can you move the hair out of my mouth? There's still hair in my mouth. It's okay. Pain is temporary, Robbie. Pride is forever. Remember that. It's okay. Oh, can you fix my hair again? Thank you, Mom. Pain is temporary. Pride is forever. No, I know. When I stop, it's going to be worse. Believe me. And the Charlie horse I am going to have is going to be something that will make I will wish I was dead.
We'll do whatever we can.
Believe it or not, it's motivation to keep going.
We went there a week ago, so it was on Friday. Little kids jump from here. It was like a 30-foot jump into the water. And the water was crystal clear. And you did have to jump out. You did have to jump out. You know, couldn't just step away. So I says, I looked at him, you know, and it's one of my So I smiled at him. He's going to be
The good life is calling your name. Your next chapter.
I was like, are you sure people jump in here? Yeah, man. The locals jump in here.
The good life is calling your name. Your next chapter could be your best at a trilogy lifestyle.
It was on the day that I just got shaved. Even then, I wouldn't go head first.
What?
First and only car
Thank you, Sarah.
built-in 4G LTE Wi-Fi to cars, trucks, and crossovers.
Thank you. Okay, sorry, that techno was too bad for me.
と変わらずに続く美しき青色で染まりして浮く司る四季たち操り隣り合う境界を切り裂いて進め新しい形があるなら今ここで満ちて花になれあやかしの全ての力をここで捧げるから戦いが高らぬ鼓動とみなぎる力が加速してくあの世界を終わらせてしまえあなたが望むなら訪れた春の始まりに心に出されてる封印の狭間が歪んで揺れているあなたには死しても見えぬ幻のあの桜どれだけかかっても答え見つけるから今すぐに時放て心を縛る鎖を今すぐに時放て心を縛る鎖今すぐに時
I'm 100 years old, and I want to tell the world what I have learned.
Hour 50 done.
Water, please. Regular. Thank you, child.
You're doing incredible, Ray. You're making me so proud. You're making me so incredibly proud. Tell me when you're done. I like how you're dancing.
I didn't notice I was.
You're not really dancing, but you're slowly switching to music. So more quickly.
But yeah, I'm gonna have such a bad Charlie horse once this is over. I might just scream. You have to warn Mom and Dad, just letting you know, because I told you I am going to have a Charlie horse like heck, and that's half of what's keeping me going. Because as soon as I stop, I am going to be in so much fine, but as soon as, well, a little bit fatigued, but as soon as I stop, I'm going to be in so much pain, I'm going to be wishing I was never born for the few minutes.
Listen, as soon as you're done, I'll show you some anti-Charlie horse tricks.
Okay, thank you so much, Robbie.
Just put your foot down and stretch your legs like this afterwards, okay? Something like that.
Okay. Okay, I love you too.
I'm so proud.
Thank you.
You are the most incredible sister.
April air humidity.
I'm 100 years old, and I want to tell the world what I have learned.
Live? It falls from the sky. It makes up 60% of our bodies, and just about every chemical process related to life takes place with it or in it. Dihydrogen monoxide. Without it, none of the chemical reactions that keep you alive would happen. None of the reactions that sustain any life form on Earth would happen. Not even the majority of inorganic chemical reactions that shape the surface of the Earth would happen. Water is the key to nearly everything, and one of the reasons it's the key is because it's really good at dissolving stuff. We need it so bad that we dump over 180 gallons of it into our bodies every year, and we do that in order to maintain an aqueous or water-based solution inside our cells. because aqueous environments are pretty much the best for cool chemistry. Each and every one of us uses water for all kinds of chemistry every single day. Our body chemistry, our food chemistry, and yes, our laundry chemistry all take place in water. This used to be a white sock. It is now a little bit of gray sock, and in places a little bit of a yellow sock. But anyway, I want it to be white again, and to do that, I'm gonna need some chemistry. To whiten whites, you might use a solution of sodium hypochlorite, better known as bleach. What makes bleach so good at its job is that it's a really strong oxidizer, meaning that the oxygen atom is really good at pulling electrons away from other compounds, making them break apart. This is really handy for getting rid of stains, but as you can tell by the formula, sodium hypochlorite also contains chlorine, which happens to be really good at killing things. That's why we use it in swimming pools and as a disinfectant. But there are lots of other good oxidizing agents, and one that doesn't contain chlorine is hydrogen peroxide, and it can be used as a bleach too. But its only components are hydrogen and oxygen, just like water. We'll talk about oxidation and other kinds of reactions in a couple weeks, but before we get to that, you have to understand solutions. And before we do that, I'm just gonna get rid of the laundry because it's kind of stinky. This bottle of hydrogen peroxide contains a solution, and not just the solution to my problem of stained laundry. By solution, I mean a solution of liquid with another substance dissolved in it. Here, water is the liquid or solvent, and hydrogen peroxide is the solute or dissolved material. And water is an amazing solvent, possibly, arguably, the best solvent on Earth. Why? A lot of reasons. There's a lot of it on the surface of the Earth. That helps. Just abundance is good. It's liquid at a very wide range of temperatures, and being liquid is what you need to be able to be a solvent. But also because it's polar. It's a very polar molecule. Remember how I said that oxygen is really good at pulling electrons toward it? Well, oxygen atoms are more electronegative than hydrogen. The oxygen atom pulls harder on the molecule's electrons than the hydrogen does. As a result, the electrons in a water molecule tend to spend most of their time near the oxygen, giving the oxygen end a partial negative charge and the hydrogens a somewhat positive charge. This polarity makes water extremely effective at dissolving things, especially other polar things. The sugar we mixed into our tea last week, for example, was polar. When you mix a polar solid like sugar into a polar liquid like water, the molecules of the water surround the sugar molecules. The negative side of the water molecule is attracted to the positive side of the sugar molecule and vice versa. And interacting with the sugar molecules, the water inserts itself between all of the individual molecules of the sugar that were once clumped together in the sugar crystals. A liter of water can dissolve as much as 1,800 grams of sucrose. Water-based solutions. Earlier, I called them aqueous solutions.
Yes,
and I'm calling it an aqueous solution again so that you remember it's called an aqueous solution. Aqueous. You can create all sorts of aqueous solutions using salts and minerals, even acids. Ethanol, which composes 95%.
I just need some bad techno soon.
Sure, just tell me when. And it has violence, Vikings, blood, death, decapitation.
Is it fast-paced?
Hi, I'm John Green. This is Crash Course World History, and today we're going to talk about one of our most worthwhile.
You want me to turn on music or Pokemon theme songs? Okay. You want me to keep talking to you, or?
Sorry, I can't. Bye. Thank you!
You're welcome.
That was tied to the record. We had another minute.
You know, that's...
My mother's worst nightmare.
What?
Rachel, a rock star?
I'm gonna have to turn on some techno about now. Dad, I might stop after 1 minute. I'm gonna have a really bad Charlie horse.
Whatever you want.
How long you planning on going, Rich?
What?
How long you planning on going?
Bring a breakfast.
I might just stop now because,
You
well,
want to round it off to the minute?
okay.
It's up to you. Whatever you want to do. You got it in the bag, Rachel. You got it in the bag.
You have the record. Just stop.
Whenever you're ready.
Yeah! You want to flip over?
I know it. I first.
If you
Well,
want to lay
2
on your back,
seconds.
and I'll stretch your leg up.
Right, you got on that leg.
Okay.
Bring what you need. Okay, all right.
Girl rage.
A little at a time. That's all.
This leg, I think.
Yeah. So we have.
Very good.
Yeah.
I actually